In 1916, Albert Einstein published the general theory of relativity. In this theory, gravity is not a force pulling objects together. It is the curvature of spacetime itself. Massive objects like stars and black holes bend spacetime around them. Planets move along those curves. But Einstein's equations contained another possibility. If massive objects accelerate, especially in violent events like collisions, they should produce ripples in spacetime. These ripples would travel at the speed of light. They would stretch and compress space itself. Einstein doubted they would ever be detected. The distortions were predicted to be unimaginably small. But the equations were clear. If black holes collide, spacetime should ring like a struck bell. Gravitational waves stretch and compress space by tiny amounts. When the first signal reached Earth in 2015, it changed the length of a 4-kilometer detector arm by less than 1,000th the diameter of a proton. That is the scale involved. Detecting such a distortion requires extraordinary precision. The challenge is not only sensitivity. It is noise. Seismic vibrations, passing trucks, thermal fluctuations, even quantum noise and laser beams, all must be filtered out. Humanity needed a machine capable of measuring distortions smaller than atomic nuclei. That machine became LIGO. LIGO consists of 2 massive observatories in the United States. Each uses laser beams split into 2 perpendicular arms. The beams bounce between mirrors suspended in vacuum tunnels. If a gravitational wave passes through Earth, it changes the relative lengths of those arms. That change alters the interference pattern of the recombined laser beams. The result is a measurable signal. The design took decades. It required advances in laser stability, vibration isolation, mirror polishing, and quantum measurement techniques. LIGO is not a telescope. It does not look at light. It listens to spacetime itself. On September 14, 2015, both LIGO detectors recorded the same signal. It lasted only a fraction of a second. The waveform matched precisely what general relativity predicted for the merger of 2 black holes about 1.3 billion light-years away. For the first time, humanity detected gravitational waves. Not through light, not through particles, through the motion of spacetime itself. This was a new kind of astronomy. Before this, black hole mergers were invisible. Now they could be heard. The universe gained a new sense. The first detection in 2015 confirmed that gravitational waves are real. But one detector alone cannot determine where a signal comes from. A passing gravitational wave stretches space in a particular direction. To triangulate its source in the sky, multiple detectors are required. That is why the network expanded. Alongside LIGO in the United States, Europe operates Virgo in Italy. Later, Japan joined with CAGRA. When a gravitational wave passes through Earth, it reaches each observatory at slightly different times. By comparing these time differences, scientists narrow down the region of the sky where the event occurred. This turns detection into localization. Gravitational wave astronomy is no longer a single experiment. It is a coordinated planetary instrument. In 2017, the network detected something new. Instead of black holes merging, the signal matched 2 neutron stars spiraling together. Neutron stars are ultra-dense remnants of exploded stars. When they merge, they emit gravitational waves, but also light. For the first time, gravitational wave detectors and traditional telescopes observed the same event. Within hours, optical telescopes around the world identified a bright flash in a distant galaxy. This confirmed a major hypothesis. Heavy elements like gold and platinum are formed in neutron star mergers. Gravitational waves provided the timing. Telescopes provided the electromagnetic confirmation. This was the birth of multi-messenger astronomy. Humanity was no longer relying on one signal channel. It was combining them. Since 2015, dozens of black hole mergers have been detected. Before gravitational wave astronomy, most black holes were inferred indirectly, through X-ray emissions or stellar motion. Now, humanity can measure their masses directly from the gravitational waveform. The signal reveals how massive each black hole was and how fast they were spinning. Surprisingly, many detected black holes are heavier than expected based on previous stellar models. This forces refinements in understanding how massive stars evolve and collapse. Gravitational waves are not just confirming theory. They are expanding the black hole census of the universe. Ground-based detectors are limited. They can only detect relatively high-frequency gravitational waves, produced by compact objects like black holes and neutron stars. To hear lower-frequency waves, such as those from supermassive black holes, humanity must go to space. The planned mission LISA will place 3 spacecraft millions of kilometers apart in orbit around the Sun. Laser beams will connect them, forming a massive triangular interferometer in space. Without seismic noise, LISA will detect waves from mergers of supermassive black holes, events shaping entire galaxies. This will extend gravitational wave astronomy across a broader range of cosmic phenomena. Humanity will not only listen to stellar remnants, it will listen to galactic collisions. Spacetime will become a full-spectrum observable. For over a century, astronomers have measured cosmic expansion using light. By observing distant galaxies and supernovae, they estimated how fast the universe is expanding, a value known as the Hubble constant. But different measurement techniques have produced slightly different answers. This discrepancy is called the Hubble tension. Gravitational waves provide a new, independent method. When 2 neutron stars merge, the gravitational wave signal reveals the absolute distance to the source. This is possible because the waveform encodes the energy released and the geometry of the system. These events are called standard sirens, analogous to standard candles in optical astronomy. If telescopes also detect light from the same event, astronomers can measure its redshift. Distance from gravitational waves plus redshift from light equals independent expansion rate measurement. Gravitational waves do not rely on traditional distance ladders. They measure spacetime directly. This new method may help resolve one of cosmology's most persistent disagreements. General relativity has passed every test so far. But most tests occur in relatively weak gravitational fields, such as within our solar system. Black hole mergers provide a far more extreme laboratory. During a merger, spacetime curvature becomes enormous. Velocities approach the speed of light. The resulting gravitational waveform contains information about how gravity behaves under these conditions. So far, every detected event matches Einstein's predictions. No deviations have been confirmed. But each detection strengthens confidence in the theory or constrains alternative models. Gravitational wave astronomy is not only discovering cosmic events. It is stress-testing the foundations of physics. And it is doing so in regimes impossible to reproduce on Earth. Some gravitational waves may not come from black holes or neutron stars at all. They may originate from the early universe itself. Shortly after the Big Bang, rapid expansion and phase transitions could have generated background gravitational waves. Unlike light, gravitational waves travel almost completely unimpeded through matter. They carry information from epochs that electromagnetic radiation cannot probe directly. Detecting this primordial background remains extremely challenging. Current detectors are not sensitive to these very low-frequency signals. But future missions, including space-based interferometers and pulsar timing arrays, aim to detect them. If successful, humanity could access information from fractions of a second after the Big Bang. Not through light, through spacetime vibrations. Before 2015, astronomy relied almost entirely on electromagnetic radiation, visible light, radio waves, X-rays. Gravitational wave detection added a new sensory channel. It does not replace traditional telescopes. It complements them. Black hole mergers that produce no light are now observable. Neutron star collisions can be timed precisely before telescopes detect optical signals. Future detectors like LISA will extend this capability further, allowing observation of supermassive black hole mergers shaping galaxy evolution. Humanity has effectively added hearing to its cosmic perception. We do not see spacetime move, but we can measure it. Gravitational wave astronomy is still young. Yet it has already transformed how we study black holes, dense stars, and cosmic expansion. The universe is not silent. And now we are listening.